All right, let's do a quick overview of white dwarfs. I know, I think I remember in the book it doesn't quite follow this pattern. I think they go right to massive stars. But since we just talked about small star evolution, I would just sort of like to finish that up. Let's just finish off small stars and tell you about everything that can happen, and then we'll go to massive stars. We already know that white dwarfs are the last stage of small star evolution, right? They are the core, the burnt out core that can't fuse because it requires 600 million degrees, something like that, to fuse the carbon. They're mostly made of carbon. I think the book says there's some sort of oxygen pollution in there or whatever. So for our purposes, pretty much carbon. Let's just think about it that way. And it's the burnout core of the star that can be white hot. So they can be anywhere from 10,000 to 100,000 degrees or so. But there's no fusion going on. No fusion reactions. It's just hot. They're just burnt out embers. So you really, if you don't want to think of them as a star, you'd probably be right. They aren't really a star like the sun is a star right now, in that there's nothing active going on inside it. We only see them because they just glow, because they're just the leftover core of a star, which is just really hot. And it takes them they have a lot of heat energy in there, and it takes a very, very long time for that to radiate out. So it takes billions of years for them to cool. So they are incredibly dense. They're really weird objects. Typically, about half the mass of the sun is a typical white dwarf. Why half the mass? For example, we think when the sun dies, it'll make a white dwarf at the center with about half of its mass, something like that. And then you're all like, where's the other half? And then I'm all like, well, those are the outer layers that expanded away. So about half the sun's mass, half a small star's mass is sort of left over in the core. So this is an object with about a third to a half of the mass of the sun in mass, but only, oops, I guess we'll capitalize our own planet, but only Earth-sized. Right? This is the radius of the Earth. So we have something with about half of the sun's mass packed into something that's only about the size of the Earth. Remember, the Earth is only 100th of the size of the sun. So to pack all of that mass into something so tiny, the Earth is tiny relative to the sun, it means these things are super dense. Remember our measures of density that we did before? Like rock was like 3 grams per cubic centimeter. Water was 1. So we had water equals 1 gram per cubic centimeter. This was our measures of density. Rock was like 3. What iron, right? This was how we talked about the planets. Iron was something like 9, right? Something like that. White dwarf, measured on this scale, is quite a bit higher. It's like nothing that exists on the surface of the Earth. It's a new stage of matter, in fact, called degenerate matter. But anyway, on this scale, white dwarf density is something like 1 million grams per centimeter cube. It's crazy dense. In other words, if you just took a teaspoonful of white dwarf stuff, it would weigh about the same as a truck. So there's nothing like it on the Earth. It kind of makes sense, though, because the weight of a star was crushing this thing for billions of years and getting it to be tinier and tinier. So it's no surprise that it's an extremely dense, small little object. Okay, remember that. Remember that it's tiny, tiny, and dense. All right, so what happens is When the sun dies, it'll leave behind a white dwarf, and then the white dwarf will just slowly cool over billions of years. So instead of being white hot, it'll be orange hot, and then yellow hot, right? And then orange hot, and then red hot, and then sort of cool off to be a brown dwarf and then a black dwarf. It'll just finally cool off to be the temperature of the space around it, but it'll take billions and billions of years for that to happen. Well, that's how the sun dies. That's the end of the story. But other white dwarfs can do really interesting things. So this is the end of the story. And then here's the deal. For single stars, that's the end of the story. So for the sun doesn't appear to have a binary companion, so that'll be it. But if a white dwarf is in a binary system, think of Sirius, one of the closest and brightest stars in the sky. Sirius has a little white dwarf companion. So here's something that could happen. And it's called a nova explosion. Here's what happens. Suppose I have a little white dwarf and then close to it, its companion is a red giant. So suppose this is red giant. So maybe when Sirius evolves finally and blows up to be a red giant, what can happen if the stars are fairly close together? What could happen is that some of this gas from the red giant starts flowing onto the white dwarf, right? As the red giant expands and expands and expands, some of that gas is going to be suctioned down onto the white dwarf. This is going to be a common story we see over and over and over again. So the gas spirals down onto the white dwarf. Why? Because the white dwarf has really high surface gravity. Surface gravity of white dwarf is high, like really high. The way to think about it is you have the weight that you do because the Earth is pulling on you with a certain amount of force, right? Why does the Earth pull on you with a certain amount of force? Because the Earth has a certain mass. Now, suppose you swap the Earth out and then put in its place something that was about 100,000 times more massive. That would be a white dwarf, right? It's a half or a third of the mass of the sun into something the same size as the Earth. So suppose someone were to swap the Earth out underneath you and then put in a white dwarf. Well, the white dwarf has 100,000 times the mass of the Earth packed into the same space. So in other words, the pull of gravity is going to be 100,000 times stronger. So you would weigh 100,000 times more. It would be like having an office building strapped to your back. So could you stand on a white dwarf? No, you would be crushed flat by the gravity. So the surface gravity on a white dwarf is extremely high because it's so compact, so massive and small. So the gas spirals down onto the white dwarf, right? What kind of gas is this? This is hydrogen gas because it's the outer layers of a star. So it's almost entirely hydrogen, 90 whatever 2% hydrogen, whatever. This gas spirals onto the white dwarf and it forms kind of an atmosphere. Now, our atmosphere is as thick as it is. How thick is our atmosphere? I don't know, 100 miles high. Our atmosphere is as thick as it is because, why do we hold our atmosphere? Because the Earth's gravity pulls it down and it hugs the Earth's surface because of gravity. So what happens if the gravity were 100,000 times stronger? Well, that means the atmosphere would collapse, right? The atmosphere would be pulled down closer to the planet. So as the hydrogen gas falls onto the white dwarf, it's squeezed by the gravity, very, very close to the surface. Well, what happens when you take this gas that was around the red giant and you squeeze it all the way down onto the white dwarf? Well, what happens to a gas when it's compressed? It's heated, So here's what can happen. H, the hydrogen gas in falling, is compressed. And it can compressed and heated. Gotta remember all my words. And heated. And can achieve 10 million degrees. That's how much it's compressed. It's compressed so much that the gas can be heated up to 10 million degrees when it falls onto the white dwarf. Okay, we'll think back to last unit. There's something magic that happens to hydrogen if it's compressed and heated to 10 million degrees. Where else do you find an environment like that? At the center of stars. So what happens is that the gas fuses. Basically, the entire atmosphere of the white dwarf turns into a giant hydrogen bomb. It fuses, boom, goes off. And so it emits a lot of light. This is light. And the whole thing brightens. The whole atmosphere of the white dwarf blows up, and we can see this, and we call it a nova explosion. People had noticed this in the Middle Ages, and especially once we got telescopes, we could see that there would be, and it always happens with these binary systems, there would be a sudden flare-up, and then it would go back down again. And the cool thing is that the white dwarf isn't really bothered by this explosion. Nothing much, it's very dense and compact. So even though its atmosphere blows up, nothing much happens to the white dwarf, and it just accumulates more matter from the red giant, and then it can happen again. These can be repeaters. Sometimes on the order of weeks or months or years, they can accumulate gas till it heats up again, and then boom, blows up again. So these are repeating explosions. Can repeat. It's very cool. So we know of several hundred, at least, maybe it's 1,000 now, of these nova systems. It's always a white dwarf in a binary system where they're pretty close together, and the white dwarf can start accumulating gas. And the gas falls down, heats, boom, blows up. And so we get this little brightening, and then it fades away. Very cool. Okay, well, the same kind of thing can happen, but white dwarfs have another special limitation, another special property. It turns out that white dwarfs have a maximum possible mass. The way to think about this is, I mean, you can't build a skyscraper infinitely tall because there'd be so much weight on the bottom of the skyscraper if you built it really tall that the whole structure would just collapse. So it's the same kind of an idea. There's only so much mass that the structure of a white dwarf can hold. If you keep dumping mass on it, the structure collapses, kind of catastrophically. And this was worked out by a man named Chandrasekhar. Oops. And this maximum mass is called the Chandrasekhar limit. So white dwarfs can't be any more massive than this. And he worked this out. I think he was like 19. He worked this out when he was really young on a boat trip. Whatever. But here's the limit. It's an interesting limit. It turns out to be 1.4 solar masses. About almost 1.5 times the mass of the sun is the upper limit on how massive a white dwarf can be. Any more massive than that, and they'll collapse. Okay, so think about this. Now, this would be a rare circumstance, right? But imagine that you had an 8 solar mass star, let's say, the limit of what we'll call a low mass star. So suppose you have an 8 solar mass star and it leaves behind a white dwarf that is maybe this white dwarf is 1.38 solar masses, right? It's really close. So it's not quite 1.4. And also, by the way, the interesting thing about white dwarfs is that the more massive they are, the smaller they are. So it's almost like loading up a spring. You know, like if you have a spring and you put more mass on the spring, it just gets pushed down, pushed down. So white dwarfs, the more mass you pack on a white dwarf, the smaller they get, more dense they actually get, which is interesting. So suppose you have a white dwarf that starts out really, really close to that limit, but not over it. So it's really, really close. And then suppose that this white dwarf is in a binary system. And then suppose that it's a close binary system and its companion evolves. And then its companion starts dumping material onto it as it evolves. Well, if all of these things work out, and granted, this is a pretty rare circumstance, but it could happen. In that case, that white dwarf could accumulate enough matter to just push it over that limit, just to tip over that limit a little bit. And then as soon as it crosses that limit, boom, the whole white dwarf collapses and explodes. Because what happens? White dwarfs are made of carbon, right? This carbon suddenly collapses and all the carbon is driven into each other and all the carbon fuses almost instantly, all the way up to iron. Why only iron? We'll talk about that next time. So it's called a carbon deflagration. The entire white dwarf explodes, not just the atmosphere, the entire thing. The entire white dwarf is disrupted. The entire white dwarf blows up. It's a tremendous fusion event. And this is called, you might guess it's more than just a nova. The nova is just the atmosphere blowing up, hydrogen to helium. This is all the carbon of the white dwarf suddenly fusing at once. This is a type of supernova, more than just a nova. And in fact, this is a type 1 supernova. In the book, it's called a type 1A. If I tell you it's a type 1, you might suppose that somewhere you're going to see a type 2, and you're going to be right. Also, if I put type 1A, that means there's also going to be type 1B, 1C, and so on. We're not going to worry about that. So don't worry about the A. We'll just worry about type 1 and type 2. Those are the major categories. So a white dwarf collapsing and exploding because it's gone over the limit is called a supernova type 1. And it's the most, with only maybe one or two exceptions I can think of, the most catastrophic event in the universe. And we'll talk about ones that are more catastrophic than that. But it's the largest explosions in the universe, supernova type 1. These are white dwarfs that collapse and explode. And when we talk about cosmology in the next couple of units, type 1 supernova are going to be really, really important in figuring out what the universe is doing as a whole, for reasons that we'll talk about. They turn out to be really, really important. But this is where they come from. So small stars that end their lives as white dwarfs can actually, with a little bit of help from a binary companion, they can actually turn into the most exciting events in the universe. So our sun isn't going to end this way. Our sun is just going to end up being a white dwarf that just slowly cools. But some white dwarfs can lead ever more interesting lives and deaths. Okay, so next we'll talk about massive stars.